So this is the second video of lecture 6, looking at structural analysis and specifically looking at method of joints. So if you're following in the PowerPoint, we're starting at about slide 7. And what I'll do is I'll very quickly talk through a general guide as to how you'd solve a method of joints question. Then we'll look at some examples. There's also a note in this bit about zero force members. So, method of joints, you're focusing on the forces acting at every joint, or the forces in every member. You may not have to solve every joint to find the forces in every member, but you'd use method of joints to find the forces in every member. You assume the whole truss to be in equilibrium, so you'd work out any support reactions at any points where it's being held down to a wall or the ground, and you'd start by finding those. The support reactions, thinking about pin joints and rolling joints and things that we've done in previous lectures. That would normally use forces, or so some of the forces or some of the moments, assuming it to be in equilibrium. You'd then pick a point to start with, usually one where there's fewest unknowns, draw a free body diagram, and start to solve and work your way around the structure, applying equations of equilibrium, some of the forces in the x and the y direction at each pin. And that will become more obvious what I mean by that as we do an example. If you look at slide 9, you'll see an example where there are some zero force members. So for instance, on slide 9 there are 4 zero force members. They're members where there is no load acting on them. There's no support reactions at the joints where they're held. So there's no loads, there's no external forces acting on them, therefore they are zero force members. If you were to remove them, then the actual structure would be possibly slightly less stable. They add to stability, but they're not actually doing anything in supporting the load. There is a question later where there are some zero force members and some not. If you're not really sure what one is, we'll identify it later. But if I just take the point F for now, from this is slide 9 still. So there's a point A down here, and there's a point E down here, and that's point B. That's a rolling joint. So, rolling joint, there's a force going that way, but there's no force in the x direction. Pin joint, there's a force that way. This force, this red force at B, which we'll call By, does not act down here. So there's no force acting in this member, therefore it's a zero force member. This red force here, which we'll call Fx, doesn't act down here. More importantly, there's no reason why there'd be an Fy force. Therefore, this force is also a zero force member. Similarly, the forces at ED, or DE and DC, they've got no forces acting on them that are there's no forces acting at D on them. There's no forces acting that can't pass through other members. There's no support forces or external forces, external loads. Therefore, they're both zero force members. So, the only force that could be acting along A, it would be your Fy. However, there is another member that can carry all that away, which I haven't drawn in. I've just added. So that's a very bad but brief example, an explanation of zero force members. And then the next slide tells us about zero force members, and if there are 3 members that form a truss and 2 of the members are collinear and there's no external load or reaction, the third member is a zero force member. So for instance, in the example that they've given in the picture, we've got two beams. DA is a zero force member. Okay, because you can see in the picture below, you can take it out, and there's still a truss for analysing that would work perfectly well. If you left these zero force members in, they'd just come out with a force of 0 at the end. So even if you're not quite sure, don't panic, because you can just leave them in and the answer will come out as 0. If we now look at example 1 for structural analysis by method of joints, that starts on slide 11, so I'll draw it and then I'll explain what to do. So first of all, we'd look, this is slide 11 in the PowerPoint if you're following it. First thing we'd do is we'd look for any zero force members, and we can see that there are no external loads, there's no forces at any of the joints that could act down BD, therefore that is a zero force member, and we can ignore it from our analysis. So the next thing you do is you may want to consider any external forces that are acting. So we might want to label these. Well, we've got a rolling joint at A, so we can only have a force in the Y direction. And at C we have a pin joint, so we can have forces here, C, Y. And I'm going to put C, X going that way to cancel out the 450 newtons. So we could start to find those, or we could focus on a joint first. We actually have enough information in this to focus on point D, joint D. So if I just redraw a free body diagram of joint D. Now, to start with, we assume a direction for these forces. So we've got FAD, and we've got FCD, and we've got 450 kilonewtons. And we know these angles because we know that we've got 4 meters up and 4 meters across in each section. So 4 and 4, we know that must be a 45-degree angle. Similarly, that must be a 45-degree angle. So that would be our free body diagram of point D. What we can now do is sum of the forces in the X and the Y direction, and solve those to find our forces. So the sum of the forces in the X direction, we're calling that X and that Y. Sum of the forces in the X direction is going to be minus 450 plus FCD cosine 45 minus FAD cosine 45 equals 0. And in the Y direction, some of the forces in the Y direction is going to be FCD sine 45 minus FAD, that should be AD, sorry, sine 45 equals 0. Now we can solve this quite easily because we can rearrange and we can say minus FCD equals FAD. Well, I've rearranged some of the forces in the Y and cancelled my sine 45s. I can then replace CD or AD in my previous equation, some of the forces in the X, so I'll do that on the next slide. So we're going to have minus 450 plus FCD cos 45 and then this minus FAD cos 45 is going to become plus FCD cos 45, because an AD was a negative CD, so a negative AD must be a positive CD, equals 0. So we can say 2 FCD cos 45 equals 450. FCD equals 450 over 2 cos 45, and that equals 318 kilonewtons. Now, we've assumed the direction of that, so we've assumed it going this way, so pulling away from the joint. Because we've assumed that, it's come out as a positive number, therefore we know our assumption was correct, so we can say it's pulling away from the joint, it must be in tension. If we then substitute 318 back into our equation, where we know FAD is minus FCD, so FAD must equal minus 318 kilonewtons. We assumed it's going that way. It's come out as a negative answer, which means our assumption was the opposite of what it is. Therefore we know that this one is actually pushing against the joint and is in compression. So that tells us two of the forces. We now have a choice. We can go and we can work at either joint A or joint C. I'm going to choose joint A because it's got fewer unknowns. Because if you remember, joint A only had a force in the y direction because it was a rolling joint. Force C was a pin joint, so it had two unknowns. And if I redraw point A, now I've drawn AD still in the original direction, so if we think it was, I drew it pulling away from, so FAD here is pulling away from point D, so acting in towards the middle of the member. Here I've drawn it also acting towards the middle of the member. Now we found that assumption to be incorrect, but I've maintained it for the diagram, and I'll show you how to deal with that in a moment. So if I draw, if I form my equation, sum of the forces in the x direction, because FAB that I'm looking for is in the x direction, equals FAB plus FAD cos 45, and that equals 0. So FAD was minus 318. The minus will then switch the direction of our assumption. Cos 45 equals 0, and we can rearrange and say FAB equals 225 kilonewtons. It's come out as positive. We've drawn it, assumed it to be in tension, so it must be in tension. Alternatively, you could have drawn the arrow knowing the correct direction from the previous section from joint D, drawn the arrow showing it in compression. You'd then not have put that minus sign in, because you'd have the number for it in compression. But that solves the first example on method of joints for structural analysis. There is now a group exercise, one for you to practice, which begins on slide 16. So if you pause the video, have a go at that question, and then come back to the video when you've finished, I'll show you how to solve it. So this is the solution. You should have had a go at the group problem solving exercise beginning on slide 16 of lecture 6. So this is the solution, or the method how you'd solve it. You'll notice one of the questions it asks is CE a zero force member? Well, you've got this 900 Newton force that is acting at a joint in the same orientation as force CE. Therefore, no, CE is not a zero force member, and you have to include it in your calculations. But the first point you start at is you start at pin D because it's got the fewest unknowns. So if we jump to a new slide, and I'll just re-sketch pin D. and this has got forces, the directions of the forces assumed. You'll notice that unlike the instructions that the lecture gives, it doesn't assume that each one is actually in tension. It assumes some are in compression. Not that that matters. And we've got this 3, 4, 5 triangle, because if we look back at our notes, we know that's 4 metres, and we know that the whole length to the bottom is 8 metres. So the big triangle is twice the size of the smaller triangle CDE. If it's 6 metres from here to here, this must be 3 metres, and if this is 3 metres and that's 4 metres, that must be 5 metres. That's where our triangle there comes from. We can then apply equations of equilibrium, and we can solve the forces in the x, and that's going to be 3/5 of FDE minus 600. So FCD is going to equal 1000 newtons. And we've assumed that it's hang on, what have I done here? Apologies, I've just spotted a typo. I've used this about 5 times and never noticed it before. So FDE, which makes more sense in the x direction. So FDE total is 1000 newtons. We've assumed FDE, which was this force here that I forgot to label, and we'll now add. FDE is 1000 newtons. We've shown it in compression. It's come out as a positive answer, so it is in compression. Our sum of our forces in the y direction is 4/5 of 1000, which was our FDE that we've just calculated, minus FCD. So FCD, if we rearrange that, will then equal 800 newtons. And we've assumed that one to be in tension. The answer is positive, so it is in tension. So now you've done that joint, you can now move on and you can work on another joint. So the next joint you'd move to is pin C. The next joint you could move to is pin C. Pin C, relatively simple to draw. We've got the 800 newtons we calculated earlier. We've got the 900 newtons that we're told is acting. We've got FCE. So the sum of our forces in the x is going to be FCE minus 900. So FCE has to equal 900. And we've drawn that one in compression because it's pushing against the joint. So it must be in compression because it's pushing against the joint. Here it's being compressed against that joint. Similarly, forces in the y direction is going to be 800 minus FBC. So FBC has to equal 800. And we've drawn this joint, this member pulling away from the joint. If it's pulling away, it must be in tension. Equals there. So it is in tension. And then finally, to find the forces in the final members, the only other joint we need to analyse in this case is joint E. So if I draw joint E and then show you how to do it. Right, a rather confusing free body diagram, not helped by the lack of clarity of this pen. But we've got the 1000 newtons that we found earlier, we've got the 900 newtons that we found in the last joint, and we're looking for FAE and FBE. We do exactly the same again. sum of the forces in the x and in the y. In the x we're going to have 3/5 of FAE plus 3/5 of FBE minus 3/5 of 1,000 minus 900 equals 0. And in the y, we're going to have 4/5 of FAE minus 4/5 of FBE minus 4/5 of 1,000 equals 0. You then have to solve those two equations simultaneously. So a couple of different ways you could do that. I'd recommend dividing one equation by 3/5 and timesing by 4/5. So if we take equation 1, equation 2, equation 1 divided by 3/5 times 4/5, or divided by 3 times by 4, whatever, you're going to get 4/5 FAE plus 4/5 FBE minus 4/5 of 1,000 minus a number that's not 900, but I can't do in my head. That equation you can then use to cancel out one of your unknowns to find the other. If anyone's stuck with that, if they email me, I'll sit and write it out longhand. But FAE will equal 1,750 newtons, and will be in compression, as we've assumed, and FBE will equal 750 newtons, and will be in tension, again as we've assumed. Don't panic if you get a negative answer and you have to say your assumption was wrong. You can still get full marks for the question. That concludes the lecture notes and the lecture video on method of joints. We'll look at structural analysis, method of sections in the following video.